Hi, everyone. Thanks for joining today. While we're waiting for the slides to just pop up and more people to get in, um, I'll start with housekeeping. Just a sec. All right, well, we are a minute after, so I'll just start with some housekeeping here. Hi, everyone. Thank you for joining today. I'm really looking forward to presenting this one to everyone. Just a couple of things. This meeting is being recorded, and that recording and presentation will be distributed by the end of the week. It will also be posted on our website by next week. I also want to give a little shout out to our LinkedIn. If you're not following our LinkedIn, we are at CA Gas Tech on LinkedIn. So give us a follow there, and you can stay updated on our upcoming webinars and projects. If you have any questions throughout the webinar, please feel free to drop them in the chat or wait till the end. You can come off mute. We'll have a little section for Q&A, and we'll also address anything in the chat then. But with that, I will pass it on to our presenter.
Perfect. Thanks, Kate. I'll go ahead and turn on my camera. So for those of you I have not met, my name's Madeline. I'm one of the energy engineers at ICF. So I'm going to be presenting this work, just talking about a GHP or a gas absorption heat pump performance mapping. And before I get in to it, I just want to, let me see. So yeah, just wanted to acknowledge some of the project collaborators. So we did this experimental study in collaboration with GTA Energy. So just have some of the folks pictured here, and then the folks from ICF that were on this project. I believe Ari is on this call, and he was pretty involved in the experimental process of this as well. So yeah, just wanted to shout out all the collaborators on this project. So brief agenda, I'm going to be discussing a little bit of the background, why we're interested in this specifically as it relates to the California market, overview of the objectives, and then the meat of this presentation is going to be focused on the commissioning of the equipment and then the steady state and load-based testing, and then how we integrated that data to develop Energy Plus modeling, performance mapping curves, and then recommendations and future work that we will be doing. And so the unit that is being tested in this case, I'll abbreviate it as GAHP, or gas absorption heat pump. It was the Rober GHP-A unit, and it's a technology readiness level 9. It's commercially available, so just kind of wanted to do an exhaustive testing. So in terms of why we're interested in this, just looking at water heating in California, it is the largest end use of natural gas. And if we look at just the magnitude of natural gas consumption, you can see here, it's pretty significant, especially in the commercial sector. So given the magnitude that can be reduced in this case, coupled with some California bills and legislation. So I have a few listed here. I won't go into the specifics of each of these bills or legislation, but if you are interested in looking deeper into them, essentially they talk about building decarbonization, energy efficiency, emerging tech, all of which are kind of back up why we would be interested in looking at this emerging technology, specifically in the California market. And then when it comes to the focus sector in this case, we will be looking at multifamily or commercial, and this is going to be for a low-rise 5 stories or less buildings. And so just highlighting some of the objectives of this study. So it is to improve the low uptake at the sector level, as I mentioned, that being commercial sector, improve low uptake at the technology level, so in the gas absorption heat pump space, and then also looking at overall technology performance in a controlled environment, so that being a lab environment where we're looking at commissioning, making sure it's performing according to how the manufacturer has published their data, and then doing an exhaustive steady state part load or transient evaluation. And then, as I said, developing performance mapping curves that can ultimately be integrated into Energy Plus modeling data. And so getting into the commissioning and the test plan, so just kind of highlighting an overview for some of the tolerances that were set for the installation and commissioning process. So any of the rates, so that being a flow rate, a firing rate, or a heating output, it was a plus minus 2%. And then any of the temperatures, so an outside air temperature, return temperature, supply, about plus minus 1 degree Fahrenheit. And following the commissioning study, it was found that the data output was within uh, the set tolerances in this case, so sufficient to move forward with the steady state testing. And so for the steady state testing matrix, it was a pretty exhaustive testing matrix that was developed, which was good because it definitely gave a holistic overview of how the equipment is going to perform and anything to look out for when integrating this technology. So 2 different flow rates were tested, 13.6 GPM and 7, and the flow rate in terms of the propylene glycol solution or the refrigerant in this case, and that was fixed at 35 volume percent. And then the outside air temperature was a range between 0 to 110, so 10 points within that range. The return temperature, 95 to 120, and 3 points within that range. And then for the part load testing, all the same metrics, just in this case, the on-run time and the off time or cycle off time were factored in given the time factor that is included for transient testing. So for the cycle on run time between 0.1 and 0.9 hours, so 6 points within that range. And then the off time 0.2 to 1 hour, 3 points within that range. So getting into the steady state testing. So before I kind of give an overview of holistically how this data looks, I kind of just wanted to highlight maybe some of the outliers that were in the that were pointed out during the testing and that I kind of just wanted to highlight and to mention. So if we look at this test matrix, essentially here, a portion of the full test matrix. So if we look at an outside air temperature at the max point, which was at 110, the 2 different flow rates for that max outside air temperature, so 13.6 and 7, and then each of the return temperatures, so 95, 110, 120 for each of the 2 flow rates, we'll see the following time series. So this is about 6 hours, and I'll split it up according to flow rate. So on the left-hand side, 13.6, kind of where I've drawn this bracket, and on the right-hand side, 7.0 GPM, where I've drawn this other bracket. So as you can see here, everything is performing according to the different parameters that are set, switching everything accordingly. But you start to see some oscillations kind of on the far right of the graph in the 7.0 GPM flow rate range. And so essentially where that oscillatory behavior happens, there's some short cycling happening in the system itself, or what is coined short cycling when you're looking at heat pump performance. And so what's happening here is that essentially the supply temperature that the Rober GHP-A unit is rated for is being exceeded, and that's been determined at a cap of about 140 degrees Fahrenheit. And this is only happening at the low flow rates. So in this case, it's just good to know to operate according to the application. And I'll touch on more on that in a bit, but just to give the other side, so essentially on the maximum side at 110, and then the minimum side, and this isn't to say the minimum side of the matrix, but the minimum side where we saw oscillatory behavior happening, and that was at 35 degrees Fahrenheit, as opposed to at the lowest point of the whole matrix, which was at 0 degrees Fahrenheit. There was no oscillatory behavior being seen at that point. And so same thing, wanted to highlight this time series, again, of about 6 hours, and where I've drawn the brackets and according to the flow rate conditions of the glycol flow rate or propylene glycol flow rate. And so in this case, same thing, just something to look out for. The Rober GHP-A unit is rated to hit a supply temperature below 140 degrees Fahrenheit. So if it is exceeded, essentially your unit won't be performing at its optimal efficiency. So if we look at a side-by-side of the two, so again, this is at 110 and 35 degrees Fahrenheit outside air temperature. The short cycling for both cases, it did happen when the flow rate was reduced to 7 GPM. And again, it's supply temperature being exceeded above 140 degrees Fahrenheit. So when you have short cycling, ultimately what will happen in the data is may lead to poor temperature control, higher energy usage, frequent repairs, or just overall insufficient system wear and tear. So it is important to, perform or operate the system according to the application that you're looking at. So in the case of this study, where we're looking at, integrating this into multifamily water heating, it would be more optimal to use a higher flow rate, just given the application in this case, and the demand or the load demand for hot water in a multifamily unit. Where you might see that the 7.0 GPM is more sufficient is maybe if you're doing pool preheating. And just to highlight too, this isn't to say that the Robert unit is not optimal at 7 GPM. It's just you want to maybe essentially configure your unit according to the application. So at this case, if you are running at a lower flow rate, you wouldn't necessarily need to achieve such high return temperatures in this case. So again, it's not to say that there's anything essentially insufficient that has come to the surface with the Rover unit. We were just performing an exhaustive test matrix, and then this kind of came to light, which I think was good because it kind of just shows the limitations and to really make sure that you're operating the unit according to what you want to achieve. And so moving forward, any of the summary data or any of the calculation data, so like COP, we have omitted any of the the short cycling data, just because we can't really get an accurate point where there's oscillatory behavior happening. And so looking at in this case, the COP versus the return temperature, outside air temperature differential. So this differential on the x-axis was used essentially as a normalizing factor. So if we look at the COP as a function of this normalizing factor, I wanted to show a side-by-side of where we have the COP gas only, where we're only looking at how does gas consumption factor into the coefficient of performance. And then we're looking at the gas plus the electric components that would essentially factor into your overall COP. And then in this case, just to mention the electrical components that really contribute, to the consumption in this case are the circulating pump and the fan components. So I wanted to show the side-by-side. If you take a quick glance at this, you might be wondering, okay, there really isn't any difference, and it's very small in this case. If we look at this, essentially the first point over here and the first point on the right-hand graph, it slightly drops where you consider both gas and electric. So just something to point out in this case moving forward. I'm just going to be looking at the COP gas only in this case. And then something else to consider, just a design consideration, just like we discussed, you want to make sure you're performing according to the application. You'll see that if you get to a higher, basically the higher the return outside air temperature differential is, the lower your COP will drop off. And so that's just, again, a design consideration to factor in. If you're falling below a COP of less than 0.9 or at 0.9, your emerging technology is essentially performing according to the incumbent technology, so that being a condensing boiler or a non-condensing boiler. So just a factor you want to make sure that you're operating at a higher efficiency than what your incumbent equipment is. And then just something else to note, so the COP behavior is most definitely contingent on ambient site conditions and return temperatures. As you can see, at a higher differential, again, the COP does tend to drop off. And it is optimal at high ambient and low return temperatures in this case. So if we look at the firing rate as a function of the outside air temperature, this was essentially modeled or simulated in order to acquire this best fit linear curve. And in this case, you'll see why in a second, but it essentially closely follows a linear behavior. Power consumption shows a similar behavior. I don't have it here in the interest of time, but it is available in the full report if you'd like to see that behavior as well. So essentially, this equation was taken as a modeled data of the experimental, or essentially a approximation curve in this case, to look at, okay, how do we take this equation, the experimental data, how do we essentially plot this on top of the manufacturer's data? So the manufacturer's data here is the green and the blue, and then the experimental data is in the red. And so as you can see, there is looking at the same essentially comparing the same span of data. So look, this is the red data, is only at a 13.6 GPM. The 7.0 GPM comparison with the manufacturer's published data is also available in the report and follows a similar trend. But as you can see here, just wanted to show one of them at least so that you could get an idea of how this data compares to how the manufacturer published their data. And as you can see, there is close alignment or close overlap between the 3 points in this case, or the three ranges in this case. So in this case, it was sufficient to move forward with the part load testing. And yeah, essentially, that's what I'll get into next. So that's talking about the load base of the transient data. So in this case, the steady state experimental data was essentially set as the max capacity when calculating part load, or the part load percentage. So to give it essentially a starting point or a max capacity, given that the steady state experimental data was consistent with the manufacturer's published data, we didn't need to use their data. We could essentially just use the steady state experimental data to just compare apples to apples in this case. And so as you can see here, this is the COP ratio, or the D rate, and it essentially implies that efficiency is relative to the load. And so here we have the part load percentage on the x-axis, the COP ratio on the y-axis. And as you can see here, it stops at about just shy of, let's call it 85% part load percentage. If we wanted to get this to continue, the part load percentage is really contingent on how long the cycling on time was run for. And so we would have to run at a longer time to reach 100%. However, it's not necessarily necessary in this case because you could model this easily, continue the curve just based on the trend that we're seeing here. And if, excuse me, at the beginning, when we were looking at how we were going to model this, it was maybe deemed that a log curve might be most efficient in this case. But as you can see here, it kind of tapers off above 1. So in that case, a linear least squares approximation was used. And that table, that tabulated table, can be found also in the report, and that is up to from 0% up to 100% part load ratio, or part load percentage. And so ultimately, between the part load data and the steady state data, this data was used to develop correction factors that were then integrated into the Energy Plus performance mapping curves. And then before I get into that, just to briefly touch on a positive finding in this case. So just to break down what's happening here. So we have the lab data, which is everything I've shown thus far on the left-hand side. And then we have some preliminary field data on the right-hand side. So I've drawn this yellow bar just to show on a scale-wise where each relates with one another. So essentially this is the same if we just look at this point, if we look at this point moving to the left, this is essentially the same scale or range as what the full graph shown here. And so as you can see, ultimately the COP steady state is reached in about 20 minutes for both, so at about here and at about here. So that was good to see that even in the field, the Rober GHPA system is operating consistent to a controlled laboratory setting. So that was just a positive finding that I wanted to highlight. So getting into our motivation on Energy Plus modeling. So overall, the objective is to forecast energy consumption, utility bills, GHG emissions, and ultimately target anyone that is interested in this data, but narrowing down that scope, it could be California policymakers, program designers, software developers, and manufacturers. And so if we look at just an overview, a brief overview of the modeling integration, overall, the individual parameters that were developed was predicted within about plus minus 5%. And I'll touch on that in the next slide in a brief in a moment. But some of the key parameters, just to highlight some of them, so that being the heating capacity and the gas use, you can see the various correction factors that were developed to account for essentially the experimental data. How do we integrate this to develop essentially input performance mapping curves that can be used to model the data that was just tested for. And so if we look at a comparison between the measured data and the model data, so the blue data is what was measured, so all the data I've shown this far, and then the orange data in this case is what was used to model the modeling performance curves that were developed in this case. So as you can see here, there's a fairly close overlap. And if we look at the percent error on the bottom, where we hover at 0%, what falls above and below that is how the plus minus 5% was determined. And then similarly, if we look at how those key parameters, how this factor into the overall modeling accuracy of the COP, only factoring in gas consumption in this case, it's about plus minus 6%. So again, looking at where it hovers at 0 and then what falls above or below that is how that plus minus 6% was determined. And so some key takeaways looking at the experimental data. So as we can see from the steady state data that was compared against the manufacturer's published data, there is very close alignment, which was a positive finding. The data does suggest to proceed according to the application when operating the unit at a low flow rate. So again, it's not to say it can't be operated at that flow rate, but just make sure you're looking at, okay, what am I trying to achieve here? What am I trying to accomplish, and operate accordingly? And then the normalized data suggests that the experimental data is sufficient for modeling integration, and that's, again, determined at a plus minus 6% error, just looking at the COP gas only. And so future studies, so taking the Energy Plus performance mapping curves that were developed for this project and using a lot of that data for a separate study that's being used to look at essentially characterizing how this would look in an Energy Plus model system. So collaborating with National Renewable Energy Laboratory, as well as using essentially the extension model for Energy Plus, so RedStock, that they've developed. So that project is very much underway and hoping to be wrapped up in the near future. So looking forward to discussing those results as well. And then similarly, hydrogen blend testing. So we've also done a blend testing up to 30% using the same Rober unit. And again, that one's also wrapping up. So looking forward to discussing those results. And then also looking at additional market-ready GHP experimental testing for ultimately to use that into Energy Plus modeling integration. So essentially looking at develop a holistic study between multiple manufacturers, natural gas only, and hydrogen blend testing to really just develop a very comprehensive comparison study. So yeah, looking forward to discussing additional projects, how this relates to essentially the base case that we've developed here with the Rober GHPA system using natural gas only. And so open to taking any questions. And then just for everyone's awareness, the program manager, Ava Donald, is also on the call if there are GET related questions.
You're all very silent today. Any sort of details that you want to know relative to the testing or some of the future testing that's planned?
Oh, I see a hand up. Jason, let me see if you can come off mute. Yes, I just allowed your mic.
Can you hear me okay?
Yeah.
Okay. I had a question about, I was really surprised to see in one of your earlier earlier plots where you showed the COP gas versus electric, and it it hardly moved, as you pointed out. I would have expected the 13.6 GPM one to move a lot more than the 7 GPM, but it appeared that they moved about the same. Can you just tell me what was the power consumption of the pumps moving 13.6 GPM and 7 GPM?
Off the top of my head, I don't know. It is in the final report though, so I can definitely get back to you on that. But yeah, I echo that the same. It was definitely surprising how minimal in this case the impact was.
I mean, your capacity was like 20,000 BTUs per hour, right? Roughly.
Mm-hmm. Correct.
Which is really small. I just remember looking at this for space applications, and 500 watts on a pump was not negligible, and that was on a 80,000. So I just would have thought that would have shown up glaringly, but it's like not. It's like a rounding error at best here.
I can definitely take a look, and I'll get back to you on some concrete metrics for that.
Thank you.
Mm-hmm.
Any other questions?
I guess I have one more question if no one else does.
Sure.
Do you have any idea what that outdoor rover unit either weighs or what its dimensions are?
That's another good question. I'm wondering I know Ari from GTI is on the call and they've installed it, or Steven, do you have any idea?
I'm thinking it's like 700 pounds, and the dimensions, I don't know exactly what they are, but it's, like 3 feet by 3 feet by 2 or 3 feet, something like that. But we got the spec sheet.
Okay.
Madeline, you could
Yeah.
email the spec sheet, which would be better in my memory.
Sure.
So are you going to do like some kind of an economic analysis, like to see if it payback and all that kind of stuff?
We definitely have discussed potentially doing a TSB, especially with some of the field data that's concurrently happening. So I think that is something that is currently in the works, hoping to get a project going soon on that.
Great.
Yeah. I could just chime in on the power draw. We didn't differentiate how much power the pumps drew themselves versus fans or the unit otherwise besides the pump and fans. But overall, the power consumption for steady state testing ranged from about 940 watts up to 1080 watts relative to the actual heating output, which is ranging up to 130,000 BTUs per hour, where the energy consumption through power was small. That's why the difference was almost negligible between the 13.6 and 7 GPM.
Sounds good.
Thanks, Ari.
I have another person raise their hand. Let's see. I think you came off mute.
Yeah, this is Ram from
Damara,
GTI.
yes.
Adlan, quick question. Could you expand on the plans for the Energy Plus integration side of things a little? Specifically, is the plan to develop performance curves or integrate these performance curves just for the GAP-A unit, or would this be extended to other models as well? Via like if the manufacturer data sets are available, let's say like for limited ambient conditions, is the plan to sort of translate that into performance curves for multiple models or different types of GAP units?
I think at the moment, we're definitely expanding on the experimental testing side, and I think we'll have a better understanding of what that looks moving forward on the Energy Plus side once some of that data comes through. But I think, yeah, overall, looking at expanding this to across multiple manufacturers where available and if possible.
Great, thank you.
Jeff's got his hand up as well.
Hey, I was just going to say on the Energy Plus side, this is Jeff McGuire from NREL. I've been doing some of the Energy Plus work. There isn't plans to add models with other data maps, but a lot of what we did kind of found and fixed some errors, and we're going to be publishing some code that makes it easier to run these models, at least in the res.doc context. So some of the stuff we did as part of this project might be useful for running other models and units, but there isn't a plan for work doing that at the time being.
Thanks, Jeff.
Sure.
And good to hear from you.
Yeah, good to hear from you too.
Sure.
Anything else? Give everyone another minute or so if something comes to mind. All right. I'd like to thank Madeline for her time and like to thank all of you for attending. And feel free to reach out if you do have any other questions that come up.
Yeah, thank you all.
Yeah, thanks, Madeline.